Hi everyone, welcome back. Today we'll be talking about centers of mass. It's a quick physical application of definite integrals that we've learned so far. And essentially what it is that if you have an object like a plate or something that's sitting in the xy plane, you should be able to pick it off of the xy plane, hold it in your hands, and then balance it on the tip of your finger at some particular point within the region's boundary. So what we're going to do is we're going to essentially dissect that into two different pieces. We're going to first look at what we call the x-coordinate of the center of mass. So I'm going to call this x bar. And what that is I pick the plate off, and instead of balancing on the tip of my finger, I instead balance it on a meter stick that runs exactly along x bar, this line right here. And I say that if it is the center of mass, then this plate won't tip left and it won't tip right. It'll instead be perfectly balanced there. I can do the same thing with y bar. So I say there's another line here that I call y bar, that if y bar is the center of mass in the y direction, then it won't tip up and it won't tip down. It'll instead be perfectly balanced in the horizontal direction here. So, sorry, I think the vertical direction there. Anyway, once we find these two centers of mass coordinates, what we can do is we can take the intersection of them, and we can be very confident that if we put our finger at that point, it can't tip left, it can't tip right, it also can't tip up or down, this way or this way. Okay, it has to be perfectly balanced at that intersection. So that's kind of nice. We took a pretty complicated problem, and as long as we're able to find these independently, then we can certainly find the center of mass of the entire object. More generally, what's going to happen in this course is we'll have two functions that bound a region, so f and g, and they are bounding the region between x is equal to a and x is equal to b, as usual. And then what we're going to do is we're going to employ a tactic of, instead of finding the center of mass of this entire thing, we're going to divide it into vertical strips like this. So there's a little bar. As usual, we denote the width of it to be dx. And then our goal is to find the center of mass of each of these individual strips. So I'm going to call that xcm and ycm. And the idea here is that if I can find the x and y centers of mass of each strip, then it's a little weird, but I can integrate each strip. So I can do one over here, I can do one over here as well. I can average by the total mass of the plate, and I'm able to find exactly this x bar that I'm searching for. And if I do the same for y center of mass, I can find the y bar as well. Okay, so what we're going to do is we're going to put together the formulas that we'll use consistently. We'll do it once, and then you can just refer to the formulas for the rest of time. Okay, but to find the x center of mass, what you're going to do is it's essentially the propensity for this object to want to tilt about the y-axis, right? So if I let this go, it's going to want to fall into the page and tilt around the y-axis if I extend a rod to that center of mass here, right? So what we're going to do is we're going to weight it by the distance of that bar to the y-axis. So I'm going to take the mass of this entire object and weight it by this distance. What I mean is simply to multiply. So the distance here is x, the distance from the strip to the axis of revolution y, and I'm multiplying that by the mass of the strip. Okay, so that's the x center of mass. The y center of mass is the same thing, but this represents the propensity for the object to want to tilt about the x-axis. So I'm going instead to look for the distance between here and the proposed center of mass of this strip. Now, if you think about it purely geometrically, the center of mass of the strip here is going to be exactly halfway along the strip vertically, right? So if I pull the strip out, I have a top, I have a bottom. We can call this 5, we can call this 1, for instance. So y is equal to 5, y is equal to 1. I anticipate that the center of mass in the y direction will be halfway through here at y is equal to 3. How did I get 3? Well, I know it's halfway between 1 and 5, but an easier way of doing it is adding 5 plus 1 and dividing by 2. That will give me the average of 5 and 1 halfway between them. So what I'm going to do here is the same thing, but arbitrarily I'm going to take f of x plus g of x at that point, right, divided by 2, and that's the distance here. That's functioning as our x like this right here, and I'm multiplying that times the mass of this strip as well. So this is what we're going to do, and then the idea is if we integrate that and then divide by the mass, then we're good to go. But the idea here is that we first need to find out the mass of the strip itself. So the mass of the strip is equal to the density times the area of the strip. The density we're going to denote as delta. The area is just the length times the width. And so we get delta. The length here is going to be the top function, f of x, minus the bottom function, g of x. So I have f of x minus g of x. And the width is going to be simply dx, right? Because that's what we denoted earlier as being this part of it. All right, so finally we have all the equations we need to write out the big ones we'll be using. If I integrate the center of mass to get x bar, what I can do is integrate from a to b the x center of mass over the entire bounds. Okay, so that will be x times the mass of the strip, which is delta f of x minus g of x dx. So I'm going to be moving this way with my strips drawn vertically. And then y bar is going to be the same thing. So I'm integrating the y center of mass over this entire bound. But this one's more complicated, right? So I have this extra factor going on here. So I have 1/2. I have f of x plus g of x coming from the y center of mass, and I have f of x minus g of s coming from the mass. It's a difference of squares that's going to give me simply delta times f squared of x minus g squared of x dx. All right, and then the very last thing we need to do, we need to normalize by the mass. So if I were to do this out, I'd get an x bar that's like super far over here, and then y bar that's super far up there. The reason being is I need to divide out by the mass of the entire object to make sure everything is normalized. So I'm going to denote the mass of the entire object as capital M, and then simply what we're going to do to find the mass of the object is we're going to use this formula here. The density times the area is what mass is, right? So this is going to be A to B. The area of that region is literally just the integral of f minus g, right? We know that. And then we need to multiply that by the density. F of x minus g of x will give me the area between the curves. And here we are. All right, so I know that was probably a long-winded explanation. If this didn't quite make sense to you over here on the right, that's okay. Maybe watch this a couple more times or look this up online, but I think the most important part here for problems is x bar, y bar, and m. So just to give you an idea of that, let's do just a quick example here. We have the region bounded between the functions y is equal to x minus x squared and y is equal to minus x. It forms this shape here. I'm going to say it's a constant density, and I'm going to say I want to find the center of mass of this object. Okay, well, the first thing to do, we know this in our three equations, we have 1 over m in all of them. So let's go ahead and just solve for m first. M, we said, is the density times the top function minus the bottom function, right? So if I'm doing this in terms of strips like this, so top function is x minus x squared, minus the bottom function is minus x dx. And then if I'm going in this direction here with integration, I'm going from x is equal to 0 to x is equal to 2. If you do this out, you get 4 delta over 3. Cool. So that's the mass. You'll be worried about that delta, but I'm going to show you why we don't care about it in a second, and why it can be 1, it could be 100, it could be a billion. And it won't make a difference where our center of mass is. So x bar is 1 over the mass. So I'm going to go ahead and just write it in the interest of time. It's going to be 1 over the mass, so it's going to be 3 over 4 delta. I'm integrating from 0 to 2 still, and then my formula says it's x times the density, or sorry, times the mass of the strip, right? So the mass is delta, and then this is f of x minus g of x. But I need to write them actually in because we have functions here. X minus x squared minus g of x becomes plus x dx. But the important thing here is that delta itself is constant, right? So I can move it outside of the integral. And then when I move it outside of the integral, they cancel out. Okay, so that's why it can be any number. As soon as it's a function of x, you have to be more careful. But if it's just a number, it cancels out. It doesn't matter. If you do this integral out, it's just a parabola. I got 1. And then y bar is slightly more complicated. But again, we have 3 over 4 delta from 0 to 2. I have 1/2, and then it's the top function squared, x minus x squared squared, minus the bottom function squared, minus x squared dx. I forgot the delta in there, force of habit, sorry, times delta dx. Again, that delta is constant, it goes away, so we don't care about it. And if you do this integral out, I got minus 3/5. Okay, so we didn't really use any of the stuff on the right-hand side over here. It's just for intuition, just to, set up the problem. I think it's good to always do that. But the important thing to do now is just check to make sure that your center of mass is actually inside of the region you were working with, right? So if we had a center of mass that's out here, that would be an issue, right? So it looks like it is. If I plot this point, I have x is equal to 1, y is equal to minus 3 over 5, which is somewhere here. That looks good to me. I mean, I feel like that could be the center of mass, so I'm convinced, and I'm going to move on to the next problem on the exam. Okay, so hopefully this was a good review of centers of mass, and that concludes, I believe, our discussion of applications of integrals. So next time we'll talk about different integral techniques and how we can use them to solve more difficult problems.